Hello, buongiorno, ahlan wa sahlan. Welcome to our next video on matrices. So, I know it's been a while since I've uploaded, but I decided to spontaneously throw in this unplanned video on matrix mechanics. Because it's a beautiful application of matrices, it'll give us an opportunity to practice our matrix operations before we move forward, and I assume that you're proficient with those operations. It'll also give you a flavor of how matrices are used in quantum physics, right? Which is something you probably, if you're watching these videos, have not gotten around to studying yet because it requires a lot of prerequisites, especially in math, but also in physics. So you're not going to be an expert in quantum mechanics by the end of this video. However, I hope to give you a good taste of how useful matrices really are in describing the real world. And hopefully we'll get lots of good, matrix operations practice in along the way. So just like in our video where we applied matrices to circuit problems, we're going to start out with a little bit of background information here. Just do a quick overview of basic quantum mechanics. Okay, so the first thing that we want to talk about is a state vector. So state vector, usually written with psi like this, between a straight line and an angle bracket. State vector is how we encode all our information about a quantum system, such as a particle or a system of particles. For instance, suppose we have an electron that's over there and has a certain linear momentum and also a certain angular momentum and spin value. All this information is encoded into our state vector, right? And so we're going to be, in order to find the probability of measuring it in a certain state, as you know, quantum mechanics is probabilistic, we're going to do mathematical operations on this state. Now, the way we do that, it looks like just this abstract object right now, and it kind of is. So in order to do concrete mathematical operations, we want to represent it in a different way. And this is going to lead us to matrix mechanics, because matrix mechanics, particularly for angular momentum, which takes on discrete values as opposed to a continuous spectrum, allows us to represent a state vector as an n×1 matrix. And we'll just say, like in this case, maybe a 3×1 matrix. With numbers inside, maybe it's 0.4, 0.1, and 0.3, I don't know. So we'll represent this with respect to some set of basis states, which are orthonormal eigenstates, but don't worry about what that means. We represent this as a matrix, and each of these entries is connected to the probability that were we to make a measurement on this state, we would find that it has a certain value, maybe one of 3 different values, and it is more likely, say, to measure it in the first value than it is the second value. And so these numbers here are connected to those probabilities. They aren't exactly per se those probabilities, but they're connected to them. Now, in general, the entries of these matrices may not just be real numbers, but could also be complex numbers, right? So they could have an imaginary component. So you could have numbers in here of the form a plus bi, where I squared is -1. And this leads us to an important connected idea with our state vector is for every state vector there is a dual vector written sort of the opposite way. So with the angle bracket on the left and the middle line, or the long line on the right. The dual vector is very closely connected to our original state vector. And to obtain the dual vector from the state vector, you simply flip this, make it horizontal like so, and then you take the complex conjugate of each entry. So if you have an entry that's a plus bi, this will turn into a minus bi. So instead of 0.4, 0.1, and 0.3, let's assume this was there was an I here multiplying this 0.1. Then the dual vector would look like 0.4, -0.1i, 0.3. This is how we obtain our dual vector. And of course, you could do the same thing to get back the original. You just flip it and take the complex conjugate of all the entries, and you have your original state vector back. And the reason we want to be able to do this is that there's certain calculations, sort of like products, like you know, in everyday life, that we want to be able to do with this. So suppose we have two different states, psi and phi, and we want to know what is the probability that a quantum system which is measured to be currently in state psi will at a later time when we perform another measurement be found in state phi. And the way we calculate this is by doing sort of a product between a vector and one of these dual vectors. So we measured it to be in state psi, and we want to know if it is now in state phi. So we write it like this, and so it's just like these two vectors, they sort of combine, right? We write them next to each other, and it's just like multiplying them. In fact, it will be, under their matrix representations, just multiplying them. And then we're going to take the absolute value, or the magnitude, or the modulus of our complex number, and square that. And that gives us the probability. So practically, what this is going to turn into is you're going to have a row matrix like this times a column matrix like this. So we're going to have a 1 by n matrix here. We're going to have an n by 1 matrix here, and we're going to multiply them. And you see that this is okay because the inner dimensions agree, and the outer dimensions are 1 and 1, which tells us we will get back a 1 by 1 matrix, or conventionally just a constant, a number from this. So we'll get back some number from this. And then in general, this is a complex number, right? It might have a non-zero imaginary part. So then we take the absolute value of this and square it, and that is a real number, which will give us the probability of our state psi, represented by this column matrix, being found later in state phi, represented by this row matrix. So the next thing we want to talk about is observables. So any sort of measurable quantity in quantum mechanics, something that we can directly probe and find that a particle maybe has a definite value for, like position, momentum, angular momentum, spin, which is sort of a kind of angular momentum, etc., etc. These things are what we call observables. There's things we can look at and say, right now, this particle has such and such a value for this. Now, for each observable, corresponding to it is something called a Hermitian operator. And you don't need to know really what this means. Just think of an operator as something which operates. It really is that simple. You know, you can get really far in a lot of subjects with a very naive view of things, I've found. So a capital letter with a hat over it is usually how we write an operator. And again, what does it do? It operates. It acts on the state vector to produce, well, another state vector. What this is depends on the operator, of course. And more practically, since we're talking about matrix mechanics here, we're going to be representing our state vectors as matrices, usually an n by 1 matrix. And this is going to be some n by n matrix. So our operators themselves have matrix representations. And so the way we're going to deal with them is very, very concrete, and that's just as some n by n matrix which multiplies your state to produce another state, right? An n by 1 or n by n matrix times an n by 1 matrix produces an n by 1 matrix, right? So another similar artifact. Now, given some particular quantum system, some particle, etc., and given some observable, some mathematical entity we want to measure about that system, how do we predict what the value is going to be mathematically? Well, you take that observable, let's say, call it A, right? It represents momentum or position or whatever. Then look at its corresponding operator. And then we're going to take that operator and sandwich it in between our state vector representing our system and its dual vector, like so. And in our matrix representation of all this, what this is going to amount to is we're going to have a 1 by n matrix multiplying an n by n matrix, multiplying then a third matrix, which is going to be an n by 1 matrix. Right, so n by n, 1 by n by n, the inner dimensions agree, so that's good. N by n by 1, again, our inner dimension is n, so it's no problem. And what are we going to end up with at the end? We're going to end up with a 1 by 1 matrix, so it's going to give us a number out of this. And this number is going to tell us exactly what value we should expect for this quantity, say position, momentum, etc., when we make a measurement on this system, like sort of an average value. Notably, this is really the mathematical concept of expected value, but physicists call it expectation value, so I will stick with that. Expectation value. We'll call this the expectation value of the observable A, whatever that is, and we'll write it as just A in angle brackets. So the observable we want to hone in on today is spin. You may have heard of particle spin before, right? Maybe you've taken a chemistry class and heard spin up or spin down, don't really know what that means. Well, that's what we're going to be talking about today. Spin, or intrinsic spin, angular momentum, as it's often called, is, as the title suggests, a form of angular momentum which is intrinsic to a particle. That is, even when there's no apparent revolution or spinning going on, it still has a value for angular momentum, which just seems to be unique to that particle and not coming from any sort of motion. So particles have this. Some particles can still have spin 0. For instance, spin 1 particles, like a photon, can have spin 0, while other particles, like an electron, which are spin 1/2 as we say, can only have 2 different values in any given direction, can be measured to have one of 2 values of spin, and neither is 0. So it's going to have angular momentum no matter what, even though it's not spinning per se, right? So for spin, corresponding to that observable, we have 3 different operators, Sx hat, Sy hat, and Sz hat, right? Which are each represented by these matrices. Now, these operators, the reason we have 3 of them instead of just 1, right? 1 operator corresponding to measuring the spin, is because at any given time, we can only measure spin in one direction. And as you hopefully know by now, the world is 3-dimensional. So if I have some vector in 3-dimensional space, or you can think of it as a point with coordinates in 3-dimensional space, there are going to be 3 components we need in order to specify that location or that direction in space. For this reason, and for reasons which we will soon see, that we cannot in fact even measure all 3 of these at the same time and have a meaningful value for them, as we will see. We have 3 different operators. So if we want to measure the spin of an electron, say in the x direction, however we orient our axes, so we have an x direction, we use this. We use this operator represented as this matrix. If we want to measure the spin of a particle in the y direction, we use S sub y hat, represented as this matrix, and the same with the z direction. Also a few other notes. Notably, if any physicists are watching, these are of course represented in the z basis. And h bar, this number right here, you may not have seen before. It is Planck's constant divided by 2 pi, also called the reduced Planck's constant. And it's just scaling this matrix, right? So we talked about scalar multiplication last time. So this number multiplies each of these values, but it's easier to write it outside sometimes than to write 0, h bar over 2, h bar over 2, 0. So this is just convenient. And the last note is that these matrices and these representations of this operator are only good for spin 1/2 particles like an electron. For spin 1 particles, which we'll deal with in a second here, we will need 3×3 matrices corresponding to 3 possible observable values of spin. Okay, I hope you made it through that. Let's move on to some sample calculations. Hopefully it will make more sense when you see these things represented as matrices, and really all our math is just going to be multiplying matrices. So, good practice for last time. So, suppose our state vector is represented by this matrix with the entries 1/√2, 1/√2. Note that both of those entries are real numbers, not complex in this case, or not, they don't have a non-zero imaginary component. So when we take their conjugates, they're going to remain the same. All right, so the way we compute this product, which we call the inner product between a state and itself, it's just the name for it. We're going to flip this on its side and take the conjugates. Of course, the conjugates are going to return the same numbers. And then we're going to multiply it by the state. Here we have a 1×2 matrix times a 2×1. So we'll get a 1×1, or just a number. 1/√2 squared is 1/2, plus the same thing, 1/2 is going to be equal to 1. And in fact, if you take the inner product of a state vector with itself, you should always get, or rather with its dual, you should always get 1. And this is because there's something in quantum mechanics called the normalization requirement that allows us to talk about probabilities. And without this being true, that the inner product between a state and itself is 1, we would not be able to properly talk about probabilities of certain things happening. It's just a requirement we have. So if, for instance, our vector was instead represented as, let's say, an n×1 matrix, where we'll just call the components psi sub 1, psi sub 2, all the way up to psi sub n, then the inner product between it and its dual vector here is going to be equal to, in summation notation, the sum from k equals 1 to n of psi sub k. So these are from the row vector. Don't forget we have to take the complex conjugate, so I'm going to mark that with an asterisk. That means a plus bi goes to a minus bi, right? Where I is the square root of -1. So this is asterisk times psi sub k. And of course, a complex number times its complex conjugate here, which is what we have in our summoned, is just going to be the same as that number modulus squared. This is just basic complex numbers, basic complex arithmetic. This is the same thing as that. And this must always be equal to 1. This is our requirement. If our state is not like this, then we have to divide by whatever this number is. In order to scale it, we have to scale every entry so that this calculation always comes out to be 1. This is called the normalization requirement. And just as a quick note, this sum being equal to 1, this requirement means that there has to be a probability of exactly 1 that something will happen should we make a measurement on this system. That is what this guarantees, right? That it's not that all options add up to a probability of 0.8, so there's a 0.2 chance that the universe just breaks. No, it has to be exactly 1 in order for that probabilistic interpretation. So sometimes we'll write our state vectors like this instead of with a psi. So it's plus y or plus z. And in this context, what this means is just simply that we measured we measured the spin of this particle or system in the z direction, and it turned out to be up, right? Spin up or spin down. Because there are two values, h bar over 2 and negative h bar over 2, of spin that our spin 1/2 particles can take on. We're going to refer to one as spin up and the other as spin down. And so what this state says is just that we already performed a measurement on this state in the z direction and found it to be spin up. Similarly here, we performed a measurement on this system and found the spin in the y direction to be spin up. All right. And then we represent these in the z basis. Don't worry about that, what that means, but these are the matrices we get, is just the point of that. So then we want to ask the question, what is the probability that, given that we measured a system to already be in the spin up state in the z direction, that when we do a subsequent measurement, it will also be found to be spin up in the y direction? What is that probability? Are they completely independent? Is there a connection between them? Let's calculate. So the way we do this is by taking the product plus y plus z like this, right? First it was found to be plus in the z direction. Now we want to know about the y direction. And then whatever this number is, in general a complex number, we're going to take the modulus squared of that number. And this is going to give us our final result, our probability. So if we do this in terms of matrices, which is what we're here to do, we're going to have a row matrix times a column matrix first. This is going to be our first calculation. So here's going to be our representation of plus z. In the z basis, this is just going to be 1, 0, as we see up here. And then our plus y vector, here, I'll just write it with the 1 over root 2 inside. So multiply, multiply, 1 over root 2, and I over root 2. Right, so we flipped it on its side, and now we have to take the complex conjugate, so this I becomes negative I over root 2 in the second entry. All right, now we are ready to multiply our matrices together, and what do we get? We get 1 times 1 over root 2, so 1 over root 2, plus 0 times negative I over root 2, which is just going to be 0. So this is just going to be 1 over root 2. And then remember, we have to take this number and take the absolute value squared, and that will give us our final probability, which is exactly 1/2. So in fact, measuring the spin in the z direction and knowing it to be spin up has nothing to do with the y direction, and we see we have exactly a 1/2 or 50% chance of measuring its spin in the y direction to be either up or down. Our next problem is straight out of my quantum mechanics textbook, Townsend, if you're interested, and it is to show that our spin operator in the z direction, as represented by the appropriate Pauli spin matrix, is equal to this mess. Now, we have not seen products like this before, but we're just going to be naive and represent it as matrices and see if it works. So we have to show that this equality holds. All right, so let's figure out what this is. So we're going to have, so plus z, first of all, the state vector plus z in the z basis is going to be represented like this, as a 2x1 matrix with entries 1, 0. Similarly, minus z is going to be 0, 1. And then, of course, we can flip those and take the complex conjugates to get our other two states, which are going to be these two. All right, so this mess is h bar over 2 times a column vector, 1, 0, then times the dual of that, which is going to be sideways 1, 0, minus h bar over 2 times, once again, column vector, in this case 0, 1, times row vector 0, 1. Now, do these products make sense? Well, at least as far as matrices, this is a 2x1 matrix and this is a a 1 by 2 matrix. So the inner dimensions are both 1, so they do agree, and we can take the product. And what we should get comes from the outer dimensions. It's going to be a 2 by 2 matrix. So that's actually going to be a larger matrix than what we started with. So let's carry out that calculation. So this is going to be equal to h bar over 2 times some 2 by 2 matrix minus h bar over 2 times some other 2 by 2 matrix. So our first entry is just going to be the product of these two, since there's no more rows and columns for us to move over into up here or down into from here. It's just going to be that product. 1 times 1 is 1, 1 times 0 is 0, 0 times 1 is 0, and 0 times 0 is 0. Similarly over here, we're going to have 0, 0, 0, and 1. And now we can, if you want, we can distribute the h bar over 2 and negative h bar over 2 into all the entries in our matrices to get h bar over 2, 0, 0, 0, plus 0, 0, 0, negative h bar over 2. And now we can add element by element here to get a final matrix of h bar over 2, 0, 0, negative h bar over 2. Notably, if you factor out the h bar over 2, you'll have it in the exact same form that I showed you earlier, was the representation for as the Pauli spin matrix, which is the representation of the spin operator in the z direction. So in fact, yes, as far as our matrix representations are concerned, this statement does hold. Our next problem is going to be find the expectation value of spin in the z direction if our state is known to have just been measured in the spin down state in the z direction. So it should be obvious what we should get. We should get that it's definitely got to be, since we just measured it in the spin down state, it's got to still be in the spin down state, no other information given. But let's see if our calculation verifies this. So the expectation value is going to be calculated via the sandwiching, remember? And now we represent these all as matrices, and we get our row vector, or rather row matrix, times our operator matrix, times our column matrix here. So in the z basis, negative z is represented as 0, 1. And similarly, if you flip it, take the complex conjugate, it's going to be 0, 1 here. And then our SZ we just showed was h bar over 2, 0, 0, negative h bar over 2. So now let's multiply out. We have a 1 by 2 matrix times a 2 by 2 times a 2 by 1. We should get a number at the end of this, a 1 by 1 matrix. So let's do these two first. This is going to be, our output should be a 1 by 2 matrix. So this is going to be 0 times h bar over 2 plus 0 times 1 is just going to be 0. And 0 times 0 times plus 1 times negative h bar over 2 is going to be negative h bar over 2. And now we can multiply these two matrices together. 0 plus negative h bar over 2 is just going to be negative h bar over 2. So the expected value that we should measure for our spin found to be in the spin down state before, if we make another measurement of the spin in the z direction, we are predicting that it will have value negative h bar over 2, which is exactly the spin down state for that direction. So again, our calculation here using matrices does indeed fit with our intuition that we just measured it that way. It should still be in that state. So last time we showed that two matrices, if you multiply them, say you have matrix A and a matrix B, that if you multiply them in this order, A, B, you may not get the same answer as if you multiply them in this order. In other words, multiplication of matrices is not commutative. It doesn't have the commutative property. Well, it shouldn't surprise you then to learn that in quantum mechanics, the operators which matrices often represent are also not necessarily commutative. Sometimes they do commute, other times they do not. And in particular, we have a device for measuring how commutative or non-commutative two operators are with each other. Right? So if we now translate this into the language of operators, we have something called the commutator of two operators, represented by these brackets. And this is just defined to be A times B minus B times A. And of course, if they do commute, if it is the same way, multiplying them in both directions, then this is just going to be 0, right? But if it's not, it gives us a sort of measure of how non-commutative it is. So, first thing we want to do is calculate with two of our most familiar operators right now. Let's take these spin operators in the x and y directions, and let's figure out, do these two operators commute or not? Do their matrices, the corresponding matrix representations, this is the way we're going to calculate it, do they commute? What is the commutator of these two operators? Okay, so here I've written down our Pauli spin matrices, our matrix representations of these two spin operators. Now we're just going to use the formula for the commutator to calculate what exactly this is. So this is going to be 0 h bar over 2 h bar over 2 0 times 0 negative I h bar over 2 I h bar over 2 0, and then subtracting it multiplied the other way, right? So we're going to have 0 negative I h bar over 2 I h bar over 2 0 times 0 h bar over 2 h bar over 2 0. And of course, we could just factor the h bar over 2 factors out. You're going to have 1 for each matrix, right? So if you want to factor it out of both and then just write it outside, that'll actually make this a little bit easier. So we could instead write this as h bar squared over 4 times 0, 1, 1, 0, 0, negative I 0, minus h bar squared over 4, 0, negative I 0, 0, 1, 1, 0. Now if you multiply these out, you're going to get I, 0, 0, negative I here. And in this direction we're going to have 0, minus I, 0, 0, I. Alright, and now we're going to have, I h bar squared over 4, 0, 0, negative I h bar squared over 4, plus, negatives cancel out, it's going to be I h bar squared over 4, 0, 0, negative I h bar squared over 4. And so we're going to have, as our final answer, we're going to have I h bar squared over 2, 0, 0, and negative I h bar squared over 2. Now, it may not be immediately apparent, but this is actually very closely related to a matrix we already know. Right? So if I erase some of this work here, this is going to be the same as, so suppose we factor out the I and the h bar and then leave another h bar over 2 on the inside. This is I h bar times h bar over 2, 0, 0, negative h bar over 2. Notably, this was this is the third Pauli spin matrix, the one representing S sub z. So we find that the commutator of these is not 0, which means they do not commute. Multiplying them either way, it makes a difference. You want to be careful about what order you multiply them in. And in particular, the commutator of Sx and xy is IH bar times S sub z. We'll come back to this statement in a bit, but this is actually a very important and profound statement. Now we're going to do something very similar. So just as spin 1/2 particles can take on exactly 2 values of spin, either up or down, spin 1 particles can take on one of 3 different values for their spin in a preferred direction. So either h bar, 0, or negative h bar. And corresponding to our 3 directions, similarly, we have 3 different operators, one for each direction that we're measuring in, and this time they're going to be represented as 3 by 3 matrices because of the 3 possible outcomes. So now what we're going to do is play with these representations of our spin operators. I've used J here to distinguish it from our earlier S operators. And we're going to find the commutator of Jx and Jy. Alright, so here's our commutator. We're going to take Jx, Jy minus Jy, Jx. So this is going to give us, let's bring our constants together, so they'll be multiplied h bar squared over 2 times some 3 by 3 matrix minus h bar squared over 2 times whatever this product is. So let's figure out the first one. 0, I, 0, it's just going to be I, 0, negative I, 0, negative I plus I is 0, 0, I, 0, negative I. Now for our second product, we're going to have negative I, 0, negative I, 0, I minus I is 0, then 0 again, then we're going to have I, then we're going to have 0, and lastly we're going to have an entry of just positive I. Okay, so and we can either distribute this inside and this inside if you want, or a better thing is to do is just to leave it out and just distribute the negative so they have a common factor. So minus I, and now we can sort of just ignore this factor because they both have it, so it doesn't matter because the distributive property, whether we multiply every entry by this in both matrices, add them, and then factor it back out, or just keep it out and do the addition with the entries of these 2 matrices. So we're going to have h bar squared over 2 times I plus I is 2I, 0 plus 0 is 0, we're going to have 0 again, 0, 0, 0 plus 0, 0, 0, bunch of zeros. These 2 cancel out, 0, 0, and then negative 2I. And we can do a little bit more with this, because you might notice if we distribute this 1/2 inside, the 2's disappear first of all. So we get rid of the 1/2, and then also we can bring the I out and bring one of the h bars in at the same time. So don't be confused by what I'm doing here. I'm just going to have one h bar here and an I, and then we're going to bring the other h bar inside. And now we have that this commutator is equal to IH bar times this matrix. Well, this matrix is exactly this matrix, right? H bar times this huge 3 by 3 with 1 and negative 1 in the corners. This is our other spin operator, the spin operator in the z direction for our spin 1 particles. so that the commutator between these two is once again non-zero. They do not commute. AB is not equal to BA here. We have that this is equal to IH bar times the operator JZ hat. And once again, so we have this identity, this funny little looking identity, where the commutator of two important operators is another operator. In fact, the commutator of these two Hermitian operators is another Hermitian operator. And I'll explain the significance in a sec. So a very similar idea that'll give you more practice doing matrix operations is going to be the anti-commutator. So it's exactly how it sounds. It's the opposite of a commutator. It is going to be curly brackets. A hat, B hat is going to be equal to A hat, B hat, not minus, but plus B hat, A hat. To what degree do they anti-commute? Now, what does it mean for things to anti-commute, or to be, to have an anti-commutative property? Well, let's not worry about that right now, but what we can worry about is computing this. And in fact, I have another problem straight out of my quantum mechanics book for you here, which is to show that from our Pauli spin matrices from before, that the anti-commutator of any two of these is going to be equal to 2 times the Kronecker delta times the identity matrix. The Kronecker delta is this special little funny function, if you want to call it that, or symbol, where it is equal to 1 if I is equal to j, and it's equal to 0 if I is not equal to j. So we'll see how this comes into play in a sec. And where sigma I and sigma j is meant to represent sigma sub x, sigma sub y, or sigma sub z here. We're just using the i's and the j's for sort of a notational convenience. So let's show that this is true by showing one particular case of it. Let's show for sigma y and sigma z. All right, so here's our anti-commutator written out between Pauli matrices sigma y and sigma z. And this product is just going to be equal to h bar squared over 4 times 0 plus 0 is 0. Then we're going to have an I, and a 0, plus h bar squared over 4 times 0, minus I, 0, or minus I, and 0. All right, and so since the constants are the same out front, it doesn't matter whether we distribute them before or after we add, right? That's the distributive property. So this is going to be equal to h bar squared over 4 times 0 plus 0 is 0, I plus negative I is 0, I plus negative I is 0, and etc. And we can distribute this in, and it will still be the 0 matrix, right? So the 0 matrix is exactly equal to 2 delta yz times the identity matrix, because delta yz is equal to 0 whenever y and z are not the same thing, right? So this has to be 0, and so anything, if a constant 0 is scaling our matrix, no matter what that matrix is, it's going to end up being the 0 matrix, right? After you multiply through by 0 in every entry. So it does hold, our statement does hold so far. All right, now if we were to do the same thing with sigma y, just with it and itself, right? The other case of the Kronecker delta is when that I and j are equal, and we should get that it's equal to 1. And our commutator should be then just 2 times the identity matrix, right? We'll see if that's the case. Well, bracketed with itself, it's going to look like this, and clearly you can see from this that operators in and matrices in general, they do commute with themselves, right? Because it doesn't matter what order you multiply it by itself in, it's going to be the same either way. So this is just going to be equal to 2 times sigma y squared, whatever sigma y squared is. Now, again, what is that? That's going to be equal to 2 times h bar over 2, 0, negative I, 0, times h bar over 2, 0, negative I, 0. Let's get all of our constants out front here. This is going to be h bar squared over 2. And we're going to have 0 minus I squared. I squared is negative 1, so minus I squared is positive 1. 0, 0, and again minus I squared or positive 1. So here then is our 2 by 2 identity matrix. You should recognize this. And then we have is equal to, so it's equal to h bar squared over 2 times the identity matrix. And now, of course, I realize I did make a mistake in the statement of the problem. The book is assuming just the matrix part without the constant in front. So this is equal to h bar squared over 4 times 2 times the identity matrix. And this is what we were trying to get, right? Is equal to 2 times the identity times the Kronecker delta, which in this case is equal to 1 because y and y are the same thing, right? So that's 1, but it was assuming without the constants out front. But nevertheless, we could easily modify our statement to say that sigma I, sigma j anti-commutator is equal to h bar squared over 4 times 2 delta ij times the identity matrix. So if you write it like that, then it is completely correct. And this is straight out of my quantum mechanics textbook too. So all you're doing is getting practice with matrix operations here, but you know, you're doing something that like we all have to actually do and learn in order to learn quantum mechanics. So it's kind of exciting that you get to, you know, get a taste of some of these problems, the more mathematical ones and the ones that are just straightforward computations like this. I think that's a unique opportunity at this stage of your learning career if you're just learning about matrices for the first time. So who cares about commutativity? After all, what do commutators and whether AB is equal to BA have anything to do with real life? Well, it actually matters quite a bit in the real world, because in quantum mechanics, when two operators commute, they share what's called an eigenstate. And what that is does not matter at this stage because we're focusing on matrices here. But what its implication is does matter, and that is that you can measure two quantities, the two observables corresponding to these two operators which commute. You can measure both observables without, in a certain sense, messing up the system. What do I mean by messing up the system? Let me give you an example. So suppose we measured the spin of an electron and found it to be oriented up in the z direction. Suppose then we made a measurement on the same particle right after that, the same electron, and we measured its spin in the x direction, and we found it to be spin up in the x direction. Then you would expect that if we were to measure its spin in the z direction, because we already measured that before, clearly we found it to be spin up, clearly nothing's changed, right? We'll find it will continue to be in the plus, it'll be spin up in the z direction. But this is actually not the case. This is some of the bizarrety of quantum mechanics, is that if you find, this is only particles which were known to be in spin up in the z direction, and then known after that to be spin up in the x direction. If you take the same group of particles, do this a bunch of times, about 50% of the time on the third measurement, if you measure this component of the spin in the z direction again, about 50% of the time you'll find it to be spin up, and about 50% of the time you'll find it to be spin down. So it's like something about this measurement caused the system to forget what its value was, what its state was back here. It changed it. So this is what I mean by messing up a measurement in a certain sense. When operators do not commute, the corresponding observables, when you measure them in succession like this, you cannot take all the information you got from all of the successive measurements and put it together to talk about your state, because successive measurements actually in some way change the values of previous measurements so that the state is in a new, the system is in a new state now. Whereas if operators do commute, you can actually make sort of, you can make observations like this and it will not change, and you can measure more than one quantity at once without sort of screwing up previous quantities. So the commutativity really does matter here in quantum mechanics. The goal then, of course, is to find as many of these operators as you can that all commute with each other. We call this a complete set of commuting observables, by which we can describe completely all information we can have at once, or the most information we can have at one time about a quantum system. This is the idea behind, if you ever heard of the quantum numbers, like you've taken a chemistry class, you have your principal quantum number, you have your spin quantum number, etc. These are 4 different things that we can know about a particle, in that case an electron, at one time, because we have commuting operators. Now, this is to go even further, because recall that we had Sx, Sy, if we took their commutator, we got IH bar S, Sz, right? These do not commute, and this is why we can't measure different components of the spin successively without changing the system. And similarly, for spin 1 particles, we had Jx, Jy. We take their commutator, we get IH bar Jz. And in fact, similar relations hold if you do Jy, Jz, you'll get Jx there, and so on. But it turns out that if you have any 2 Hermitian operators in quantum mechanics, operating at an abstract level here, if you have any 2 Hermitian operators and you take their commutator and you get I times a 3rd Hermitian operator, any time that this holds, which is both of these cases but also in many more cases, anytime this relation holds, it's going to imply via the Schwarz inequality, in a derivation that is not important to this series, it's going to imply that you have another relation that must hold, which is this. This is what's called an uncertainty relation in quantum mechanics. And no doubt you have heard of a very particular case of this, the Heisenberg uncertainty relation. So because this relation holds between these spin operators, say, then the uncertainty in the angular momentum in x and the uncertainty in the angular momentum in the y direction, that's what these quantities represent, if you multiply them together, there is a lower bound for them, which is the expectation value for the angular momentum in the z direction. Take the magnitude of that and then divide by 2. That is to say that the product of these 2 uncertainties has a lower bound, which means that you can't have complete knowledge in a certain sense. Depending on your interpretation of quantum mechanics, either you can't have complete knowledge of the system at any given time, or it just doesn't have definite properties at a given time, or whatever. Simultaneous definite properties here between these 2 and these 3 properties. So this commutation relation is really important in that it implies an uncertainty relation. Similarly, there's a very similar relation, position and momentum in that cardinal direction so x and p sub x is equal to IH bar times the identity operator. The identity operator is just the operator represented, if you want to think of it this way, by the identity matrix. And it turns out that the identity matrix here is also a Hermitian operator, although in the most trivial way possible. And this implies an uncertainty relation between position and momentum, namely that the uncertainty in position times the uncertainty in momentum in that same direction. The product of those have a lower bound, namely it is going to be h bar over 2. And this is Heisenberg's uncertainty principle or uncertainty relation, right? So commutativity and whether two matrices multiply in one order and in the other order and get the same product, these things actually have huge physical significance and imply the Heisenberg uncertainty relation amongst other relations. There's one between energy and time as well, and others, but I digress. So this has been a lovely little discussion of introductory quantum mechanics and how matrices play into that. How useful matrices really are, because you're not ready if you're watching this series and learning about matrices for the first time. You're probably not mathematically or physically mature enough to study quantum mechanics in its full glory yet. However, it's really nice to be learning about these things and to see how useful they really are, how matrices have vast real-world connections and applications. So I hope you can at least get a flavor of that from this video. And if you didn't follow any of this, that's totally fine. We will be back to our regularly scheduled programming with the Matrices series very soon. And we will continue with our matrix operations unit. Also, if you are further along and you would be interested in me doing a series on quantum mechanics, from a physics perspective, not as much from a applied matrices perspective, just leave a comment below and I will consider doing that. Have a wonderful day.